All right, we're now going to calculate the electric field from this little Coulomb charge here. And when we want to calculate the electric field, that's simply going to be this formula. And I will actually put in my number, so that's going to be 9 times 10 to the 9th times -2 times 10 to the -4th over 0.05 squared. I'll put some brackets around that so you don't think I'm trying to subtract anything. And so when we're actually done with that question, I ended up getting 7.2 times 10 to the 8th newtons per coulomb. That's the unit on the electric field. Now, we've got a 2 times 10 to the -6 charge placed in an electric field with this strength. We want to know the net force and charge and what its acceleration if it has this mass that's given here. Let's go ahead. So when I give you an electric field strength like this and a charge, you can simply use the formula F equals Q times E. So we'll take in. I meant this to be positive 6 there. So we got 2 times 10 to the -2 times 10 to the -6 times 5 times 10 to the -6, positive 6. Sorry, when you actually put that in your calculator, you're going to end up getting nice, simple 10 Newton force. Now for the acceleration, let's remember that F equals ma, kind of bringing it back to first semester. So we're going to have a 10 Newton force equal to 0.02 times A. And when we simplify, we're going to end up getting A equals 500 meters per second squared. All right. Now part C. I absolutely love part C as a question for G period. I don't think they're as happy about it though. Sorry, I don't know why I snickered like that. I felt like that was like an appropriate teacher move to snicker. All right, here we go. So we have a tension in this rope. And although the electric field points this way, clearly the charge is being pulled out this way. So that's the electric force. And we have a force mg pointing downwards. So this is a free body diagram problem. What we're actually going to end up having here is we're going to have t cosine theta as the horizontal force. And you know, that's Fe. And then the vertical force is going to be t cosine theta. So here's the idea. I actually have, sorry, that's not t cosine theta. It's t sine theta vertically, t cosine theta horizontally. And what we're going to do is we're going to balance forces in the x and y direction. So in the y direction, t sine theta balances mg. And in the x direction, t cosine theta equals the electric force, which in this case is going to be Q times E. So the first thing, I'm going to actually get the angle first, okay? And I'll tell you why, because it actually allows me to do a little bit of subdivision. So I'm going to take these formulas here, and this formula here, and I'm going to do something very, from a physics perspective, pretty slick. I'm going to divide these two formulas. These t's cancel. Ooh, and look it. We get tangent of theta equals all of this number mess here. Now we put in our numbers. 0.2 is the mass. G is 10. I made a little bit of a typo here, everybody. I'm sorry. I wanted this to be plus 6 for that field. So that's going to be 2 times 10 to the -6 times 8 times 10 to the +6. So that gives us 2 over 16 for the tangent of theta. So theta is going to be the inverse tangent of 2 over 16. And when I worked that out, that got me about 7.2 degrees. Now we can actually go and get the tension force. So T times sine of theta, that's T sine of 7.2, equals mg, which is going to be 0.2 times 10. So T is going to be 2 divided by the sine of 7.2. And when we work that out, that's going to end up being, oh, got to get my calculator out. Bear with me, everybody, because I'm too lazy to pause this video. Sorry about that. All right, so the sine of 7.2 is 0.12, and when I actually take the reciprocal of that, 2, I'm getting about 15.97 newtons. That's cute. I guess I'll buy that. Why not? All right, everybody. That is the, that's actually question 5 on electric fields.